All right, so I'm pleased to introduce today Stephen Pestana. He got his bachelor's degree in geology from Cal Poly Pomona. He then worked as an intern at NASA with Develop, doing lots of remote sensing work. And he came here and he showed up in my office one day and said, I'm in this master's program and I have some work study, and if you just got any random work for me, like I have work study and I work really cheap. And I said, great, sure, I'll do some random work. And then Stephen had done more in his random hourly work than all of my like paid RAs had done in a whole quarter that you, they're online. Master's program, you need to get a PhD because you're way too down. So we finished his master's in 2019. After that, the world shut down, and it's been a hard go for all of us. Stephen stepped up a whole lot during the pandemic. He took over in fall of 2020. He completely taught independently my data analysis lab while I was on sabbatical, 100% online during the pandemic. He redid every part of that class, converting it to Python in interactive format, and is what I just still use today. It was admired so much by the university in terms of his teaching that he got the 2021 College of Engineering Teaching Award. And he's volunteered all over in terms of SNOWX Hack Week, Water Hack Week, SNOWX fieldwork. He served on the grad student advisory board through the pandemic time, trying to get everybody back on campus. He also, you can see him around town working as a naturalist, and he used to tell me when I should bring my kids to see salmon in the Cedar River because he's a volunteer with the aquarium and goes and teaches people about the salmon life cycle on the weekends. And he is now going to explain to us how very happy goes east and not so happy goes west. I'm sure are going to view the world of snow and trees from far out in outer space. And if you haven't got to play with the Legos, they are very cool. And so with that, I will turn it over to Stephen.
The 17 out of place.
It's sad.
Yeah, it's still up there. But I did. So yeah, thanks everyone for coming, and thanks for those of you online, family and friends, colleagues tuning in via Zoom. Yeah, today I'm going to tell you all about the work I've done here with remote sensing of mountain snow surface temperatures using geostationary satellites at high temporal resolution. In this talk, I'm going to go into an introduction and give a lot of background information about this topic, and then detail the project in 3 parts, the 3 chapters here, and wrap up this conclusion. So, you know, as hydrologists, we'll, love the water cycle. This is actually a poster in Wilcox now, which is awesome. I like looking at it. But specifically, part of the water cycle I'm interested in here is up in the mountains at the top of the terrestrial water cycle, the snowpack up here. The snowpack is important because over 1.9 billion people around the world depend on water resources that are flowing down from melted snow in the mountains. And the snowpack in the mountains have been termed the water towers of the world because they actually serve the natural storage for water. So precipitation falls in the winter, stays there as snow, it melts in the spring and summer, flows downstream, supporting water when we need to water our crops, keeps a lot of cool for aquatic ecosystems like salmon.
These men accused of robbing multiple 7-Elevens around Cape.
Thanks for your input. This snowpack, a lot of the snowpack also overlaps with forested areas in
More police officers.
In Western North America alone, 65% of the snowpack is in forested areas. And of course, we want to be able to make predictions about this snow, when it's coming, how much it's going to have. We really want high temporal resolution observations to help these models to improve them so that we can get better predictions of snow or water resources. High temporal resolution observations really capture like rapid transient events like inversions, melt freeze cycles, because all of these can cause uncertainties in our model of snow surface temperature, uncertainties in the surface energy balance of the snow, which lead to uncertainties in when we think the snow melt's going to occur and at what So we can use satellites to observe large areas all at the same time. But there are trade-offs between the spatial resolution of the images you get and the temporal resolution you get. And so on the plot on the right there, I'm showing snow temperature measured over time. That's that black line. And then there are 4 dots on there, the blue and red dots. And those are a couple of satellites flying over it. They also measure snow temperature. You can see that they got fairly good, but they only got 4 measurements. You can't really capture like really fast processes that are happening on the surface with just measurements a day. And on this plot, I'm just showing examples of some satellite imagers and their temporal and spatial resolutions. And so what we're interested in is getting that high temporal resolution, which comes at the cost of spatial resolution, and we end up wanting to use geostationary satellites to capture that. So what do I mean when I'm talking about geostationary satellites? So, okay, here's the Earth, and around the Earth, we might have, some satellites in low Earth orbit. They can maybe get us some nice high resolution images. However, out in geostationary orbit, 35,000 kilometers away, these satellites orbit the Earth once every 24 hours, the same amount of time it takes the Earth to rotate, which means they're always looking straight down at the same spot on Earth. And that allows them to just take images over and over and over and get near real-time observations of the same hemisphere of Earth. So you can start to get an idea of why they are for spatial resolution. If you're further away, and then zoom in that camera more. But they get you images like this. So these are images from goes west and goes east. These are 2 of NOAA's operational weather satellites that they use, and the instrument on board the advanced baseline imager. It's got bands going from visible to infrared, and they get 5 to 10 minute repeat imagery here. But you can see I've outlined Western and continental US there. The satellite's not looking straight down anywhere on Earth except right at the equator, right where it's orbiting. And so everywhere else we look, like Western US, it's off at some odd angle. The Earth's curving away from the satellite. So looking at all these odd angles everywhere else on Earth, and zooming in and looking at some of the thermal imagery from this, this is just downloaded from the National Weather Service the other day. These animations, we can really see that, of course, 2 kilometer spatial resolution, and these odd off-air view angles. You can see how the outline of the states are oriented in directions here. So we can get some idea about what are the anticipated challenges of using geostationary satellites to make these sorts of observations. So on one hand, we have our off-meter view angles and the parallax effect I'll get into. And then we also have our forced spatial resolution and mixed pixels. I'm first going to talk about these mixed pixels, what I mean by that. So we're interested in scenes like this. This is an image from the drone, got a couple of trees. These are warm trees in the thermal image, they're full of snow. But as we decrease our spatial resolution, we end up having fewer and fewer pixels covering this area. We end up with just one temperature measurement for this whole area. Some mixed pixel. We have multiple temperature end members in that pixel that we're interested in, but we only get one mixed signal coming out of that. So now I'm going to shift and look at spectral radiance plots. So I'm plotting the wavelength here on the x-axis, visible through thermal infrared, the y-axis radiance. Since all surfaces are emitting electromagnetic radiation proportional to their temperature, we can describe the total radiance they emit with the second Boltzmann equation under the curve there. And that's actually quantifying that area under the curve, the total emitted radiance. Whereas the spectral radiance, the Planck equation up there, is telling us at some given wavelength, at one particular wavelength, what is the radiance that is being emitted there. And I've drawn 2 curves for 2 different surfaces, so one at 0 degrees, one at -23. And this is just showing that the total radiance increases with increasing temperature, but also the peak radiance shifts towards shorter and shorter wavelengths. And this is important because one method for overcoming that spatial resolution problem is to use a linear unmixing model to try to tease apart those 2 temperature end members. This has been demonstrated before for different applications, including for snow and forests here. However, this requires us to have observations at multiple wavelengths in waves and thermal infrared. And you can also see that besides the radiance emitted by the objects that we're going to be that we want to solve for, we also have to contend with reflected solar radiation. So we're talking about infrared, so where's solar radiation coming in here? Here are our curves with wavelength, and I've pointed out some of the spectral bands in the GOES satellite instrument. And one of these in the mid-wave infrared overlaps with solar radiation coming down through the atmosphere. So the sun, although its peak radiation is in the visible wavelengths, there is a small amount in the mid-wave infrared. And so if we need to use observations in the mid-wave infrared, we have to contend with both the reflected solar mid-wave and the surface emitted mid-wave infrared radiation. Whereas with the thermal infrared, we don't have to contend with the emitted. So these other challenges that we have with view angle and the parallax effect. First, I can define the parallax effect. That's where if you're viewing a scene from two different angles, you can have an apparent horizontal offset. If you have something like a mountain here, viewed at two different angles, you project that onto an image plane, the top of the mountain will appear in one spot to this purple satellite here, whereas that orange satellite, the top of that mountain projected onto an image will appear over here. So you're basically looking at the size of the objects. And this occurs at large scales and small scales, but on the same thing there happening with, we have a mixed pixel of trees and snow. From one view, you're seeing the tops of the trees. From the other, you're seeing more of the sides of the trees, which are concealing some of that snow surface behind them. And so here's some examples of what that looks like. Just this great image of Denali in Alaska. You can see we're viewing it from GOES east. Alaska is way at the edge of that limb of the earth that we're able to see. So we're really just looking at the side of the mountain here, not looking down on it. And then at the scale of individual trees, this thermal infrared image is showing how looking straight down, we can see the tops of the trees and snow gaps between them. But as we start looking at further and further off greater angles, those gaps in the forest become hidden by the trees. We're now just looking at the sides of the trees. And so that temperature we're seeing starts to become biased warm the further we look out there. However, this is all changing over the course of the day because the sun is moving across the sky. And even though I'm not talking about reflected light yet here, the sun is warming different surfaces that are sunlit more than other surfaces that are shaded. And so depending on what orientation we're looking at a scene and where it's being illuminated, we may be seeing more of the warmer sunlit sides or the cooler shaded sides of that scene. Again, at different spatial scales. So to consider those two together, the view angle and the solar illumination angle, I'm going to use this phase angle, which ends up being the angle between those two vectors here. And so for our geostationary satellites, because the satellite is essentially fixed in the sky relative to some point on the ground, we only need to think about during the daytime as the sun is traversing the sky and how that phase angle changes. In the visible and near infrared and shortwave infrared, this is a well understood process and it leads to phenomena such as shadow lighting. So if you're taking a picture of a forest here and the sun is passing the sky as it approaches a phase angle of 0, so as the sun is directly behind you, all the shadows that it's casting are completely on the other side of the objects that are casting those shadows. So you're only seeing the sunlit side, and that's what that little model is for. You play with the flashlight, you can put the flashlight behind your head and get the shadow height here. But this is in the visible and near infrared wavelengths here. We're going to look at this later in the mid-wave infrared to see how the reflected mid-wave also may be exhibiting this effect. So here are the challenges that we want to address for using geostationary satellites to observe snow and mountain and forested areas. This was a lot of information, but to summarize it up, we've got chapter 1 will cover these large spatial scales, the size of the mountains. We're going to be looking at thermal infrared. So this is just emitted radiance. In chapter 2, we're going to zoom in and look at smaller spatial scales, the size of trees. And again, still looking at thermal infrared and emitted radiance. And in chapter 3, we're then going to stay at that scale of trees, but we're going to shift to look at reflected mid-wave infrared rather than the emitted. And these will be covered in my 3 chapters. So we'll be ready to go. But pause, check the time. So chapter 1 is about, we evaluated GOES heat brightness temperature observation biases over the Center for Standard Data in California. This was published last year in Remote Sensing of the Environment. And in this work, we wanted to know, can we correct that parallax effect that we're getting with the terrain in the GOES east imagery? And how is topography, how is that those large scale, mountain size surface roughness, how is that biasing our observations when you compare them to other satellites that have a straight down layer? So to study this, we looked at the Sierra Crest in California, between Tuolumne and Mammoth Mountain. And we used data from these 3 imagers. So we have our GOES East ABI imagery, thermal infrared at 2 kilometer resolution, MODIS imagery at 1 kilometer, and then ASTER, which is at 90 meters. Now, MODIS and ASTER are on the same spacecraft, and so we can get images co-located with those 2. And every time the satellite flew over our study site, we've got 500 images in this from 2017 to 2020. We grabbed the GOES image from that same time, and we ended up with these image triplets. So 3 images of the same site at different spatial scales and at different viewing. To orthorectify the imagery, I wrote a Python utility that forms this. Orthorectifying satellite imagery isn't new. It's a standard thing, even in aerial imagery. And so really what was new here was applying it to GOES. It hadn't been applied to any of the standard data products, given that it is a satellite used by weather forecasters. They're not typically interested in looking at surfaces in this kind of detail. The other thing that was new was rather than orthorectifying and correcting this with an elevation model that was the same spatial resolution of the satellite imagery, so it's 2 kilometer scale. We did this at a sub-pixel level, basically draping those big pixels over a finer resolution terrain model. And that's because we know mountain terrain is going to vary a lot just within a 2 kilometer area. And so we wanted to improve our ability to geolocate this imagery and compare with other satellite image products. And so correcting the imagery looks a little something like this, where you can see we shifted those mountaintops, we applied that horizontal displacement, or rather they were displaced horizontally and corrected for that now. So we can go ahead and do a comparison for all our GOES images against all those higher resolution ASTER images. We can see that they're biased warm, and there is a lot of spread between the surface temperatures that we're reporting in our study area. After we orthorectify those, we still have a warm bias, but most notably that spread is greatly reduced. We kind of have more just like a constant offset between our observations. So this was a great result. We're really happy with this, that we could properly align these images and continue with this analysis. We then saw that at nighttime, these biases were not nearly as great as during daytime. And so we wanted to then investigate, okay, what's the sun doing in the daytime? Why are we getting this warm bias in the day? What's going on here? So what we did to analyze this is we took our digital elevation model and used it to classify all of our study area, whether by whether the slope is facing the satellite, facing away from the satellite, or even for parts of the terrain that are just completely occluded. So they're just behind another mountain and the satellite can't even see that area. We then have the same with the sun, where the sun is illuminating the scene, and then the intersection between those 2. And we looked at how the imagery compared in each of these classes and found that the GOES imagery that was captured or was best capturing the surface temperature of mountain slopes that were solar illuminated and were facing the satellite. We were seeing more of these slopes that were illuminated and warmer and facing our satellite than say the slope that we're facing away from the satellite, and especially the slopes that the satellite actually couldn't see at all. So in this chapter, we demonstrated how to orthorectify GOES ABI imagery using a sub-resolution DEM. And then we also showed that the surface brightness temperatures were matching our other satellite observations more closely for those satellite facing and solar illuminated mountain slopes. So in chapter 2, we now want to look at sort of all these same things, but on a much finer spatial scale. We're going to be looking at the scale of individual trees rather than mountain side to side of the mountain. In this work, titled it Snow and Forest Temperature Observations during the Snow 2020 Grand Mesa Field Campaign and Thermal Infrared Shadow Lighting. Get into that. So what are we looking at here? Here's an example of a scene, north to the right in this image. We've got trees and snow. Those trees are casting shadows onto the snow. The trees are casting shadows to other trees. If we think about, okay, what might be the temperatures here? The snow out in the sunlight is warmer than the snow in the shade, and the trees in the sunlight are warmer than the trees in the shade. And so if we're using goes east, moving from this direction in this case, we may only be seeing those sunlit sides of the trees. And it may actually be concealing the shadow of colder snow surfaces behind the trees. Whereas goes west, seen from the other point of view, may be seeing both the shaded areas and the sunlit areas. And here's a thermal image of the same area on the right, a visible image on the left. And then a transect of the temperature across that thermal image. We can see that when the study took place, we had like huge 10-degree temperature differences between the really cold snow in the shade and the warmer snow out in the sun. And so we're looking for a signal here between the GOES observations and the presence of forest and view angle as the sun traverses in the sky. And want to know, how do these biases change in space with increasing forest cover versus just looking at open snow areas? And second, how do they change over the day with the sun traverses the sky? So we're going to be investigating all these things. We're going to be using different observations, goes east and west, giving us different views, as well as satellite and airborne infrared observations to give us that data looking view. We'll have ground observations. We want a nice big flat area with varying forest cover across it. Luckily, NASA was conducting the Snow 2020 field campaign, and so as a part of that, we collected imagery over Grand Mesa in Western Colorado. This is an astro image showing what the mesa looked like at the time we were out there. I'm digging a snow pit and taking a density reading there for a different project, not this one. So the data we collected while we were there, or the satellite data that we're using, we have goes east and west. And then we have an astro image. Astro flew over on one of the cloud-free days we had there over imagery. And then we have this fantastic data set of airborne infrared images. So this data set gives us a sense in space and in time how temperatures were changing across the mesa. So this example here is showing on one morning, February 11th, across this 1 kilometer square area out on Western Grand Mesa, snow surface temperatures warming up in the morning. And then we have ground data. So riding out snowmobiles, there I am setting up. The tripod behind me is actually a radiometer, measuring snow surface temperature. We'll see data from the radiometer in a moment. But to orient us here, here's Grand Mesa and Google Earth. Those purple pixels, or the purple outlines, are GOES 17 pixels that are on top of the mesa that we'll be using. And then we're going to shift to the view of GOES east, or those orange pixels we're going to be seeing. And then now I'm going to shift into just a map view. So you can see these pixels have been rectified and draped across the terrain. There are these big funky shapes. These are the zones that we'll be sampling in the study here. So as part of the experimental design for this, we have our GOES pixels. We want to sample temperatures with it. And then we have in the blue dashed lines the tracks the airplane was going to fly. And then we have some ground points here out in the Western Mesa with the flooding snow surface temperatures as well. And we have our range of fractional forest cover across these pixels, going from 12% out in the west and almost half of the pixel being forested over in the east. So to compare all these data sets, every time the aircraft flew over, or when our satellite flew, that Aster 90-meter resolution satellite flew over, we clipped those images to each of these GOES pixels and then compared, what's the temperature seen by the aircraft or the satellite at this higher spatial resolution against what was the 1 pixel temperature measured at that time by GOES. And so we did this comparison across all those pixels. We had 2 cloud-free days with airborne observations. When this we also had to ask it flying overhead. So we were able to do this comparison, lots of data here. I'll just show you one result here. So from one set of pixels, we can plot, we have 2 days here on the tops. The 8th of February and the bottom, the 11th of February. We have our ground-based snow surface temperature observations in that black line. So snow warming up over the rest of the day, we'll be back in the afternoon. We have the Asker satellite overpass, that red diamond in the top block there. And then each time the airplane flew over, I have one of those blue dots indicating the temperature that it measured for this whole area and a standard deviation of the temperature across the area of the bars. And then we have our GOES satellites, the purple and orange there. So the temperatures that they were measuring across the site at the same time. So we wanted to know, these all they don't quite line up here. They're not all showing the same temperature. So we wanted to know, are those warm biases we're seeing, GOES is showing a warmer temperature than we measured on the ground. Are they correlated with how much forest is in our pixel? And what we found was, here I'm showing on February 8th, the temperature difference between both GOES West and GOES East, between the airborne and Asker imagery. And we see here that GOES West, those temperature differences plotted against the fractional vegetated area. They are not sensitive to the fractional vegetated area. The differences were all about the same across the basin. Whereas for GOES East, we see as our fractional vegetated area in the pixel increases, we get warmer and warmer biases. And we see the same pattern occurring from the 11th with airborne imagery. And I want to note that the time that our aircraft was flying on both these days was the mornings. We had flights until about 1 o'clock most of the time. So these are all for morning observations, which we'll see on the next slide. I'm plotting these differences now over time, rather than the fractional vegetated area. And so all our airborne observations are in the mornings here. And we can see the purple line there is, or the purple dot, they're comparing GOES East and GOES West. And we can see in the mornings, the 8th is a little noisier than the 11th. We can see in the mornings that GOES East really has this warm bias compared to all their data sets reflecting. But then in the afternoon, this relationship flips. Although the only observations we have about the GOES East and GOES West, we didn't have aircraft flying in the afternoons or other satellite passes there. So we see this relationship flip. So we saw that GOES 16 was biased warmer due to more forest cover in the mornings. But it seems like this is flipping in the afternoon. So what's going on here? Well, remember back to when I introduced the phase angles. You have to think about the sun traversing the sky. Where's the sun in the morning? When GOES East is viewing this area. It's in the southeast. It's illuminating the area from the same direction the satellite viewing this area. Whereas where's the sun in the afternoon? It's in the southwest now. So now it's illuminating the area from the direction that GOES West is viewing the scene. So if I go ahead and plot the time of that minimum phase angle reached on each day, we can see that that coincides with when we get the maximum differences. For GOES East in the mornings and GOES West in the afternoons. So to try to illustrate this a bit better here, here's one of our plots. We have the morning sun over in the east. GOES East is only seeing sunlit surfaces. GOES West can see our sunlit and shaded surfaces, and our aircraft is also seeing their sunlit and shaded surfaces. Whereas now we're in the afternoon, and GOES East can see the sunlit and shaded surfaces, whereas GOES West now only seeing those sunlit surfaces. It's those shadows are hidden behind the objects that are casting the shadows, the trees in this case. So in this chapter, we saw that in the mornings, the GOES East brightness temperatures were biased warmer in more forested areas, but GOES East and West were each biased warm at the time that the sun was at its minimum daily phasing. So this is now a time where I take a drink of water, take a breather. I feel like I've been digging in a snow pit here. What have I been talking about? I see some of you falling asleep. Yeah. I was just talking about thermal infrared observations. So these are all, this is all radiance emitted by objects based in proportion to their temperature. And so these shadows that I'm talking about that are being hidden aren't the shadows that you and I see. Rather, it's the thermal footprint that is the result of a shadow being passed. This visible sunlight is being blocked in an area that will remain colder. And so that is now a thermal shadow there. I'm going to shift and we're going to talk now about reflected light. So this still isn't visible light. This is reflected mid-wave infrared light. And we're going to be looking at the same study area. So you're already familiar with Grand Mesa. I'm going to be talking about the diurnal mid-wave anisotropy that we observed over snow and forest with those good as observations. And this work was just submitted to library 2 days ago. So remember our spectral plot here. We have our wavelengths, we have our radiance in red. We've got our sunlight coming down. We've got some cold surfaces in the blue lines, and we're interested here in the mid-wave infrared area. But this solar spectrum here, that's not all going to get reflected from the surface. In fact, very little of it's going to get reflected. A lot of natural surfaces, like snow vegetation, have low reflectance in the mid-wave infrared. So we have to zoom way in here. We're zooming way in. This is that same blue line for the strength of receipt Earth. And now this green line is a small percentage of that red line, of that solar spectrum that is being reflected by our snow and forest surface. So, but the satellite doesn't know what is the midwave infrared that it's seeing that is reflected versus the midwave that it's seeing that's emitted. It's just measuring all the midwave that comes into its camera. And so what it's seeing is this black line, just an estimation of this. So we want to know, are snow and forest exhibiting the shadow hiding effect in the midwave infrared that we saw in thermal imagery that was just emitted, whereas now we're talking about reflected. And we know that this happens with reflected sunlight in the visible and near infrared spectrum. So we're looking for this in the midwave infrared now. And we want to know, can we find hotspots like this where phase angle is close to zero, we get an increase in reflectance? Can we find midwave infrared hotspots using that phase angle to predict when they will occur? And are those hotspots, are the magnitudes of those hotspots greater in areas with more forest cover? And how do they vary between the open snow areas and the more forested areas like we saw in chapter 2? So again, we're at Grand Mesa, again, using those east and those west observations. But now we're going to be using, in addition to the thermal infrared, here also going to be using band 7, which is the midwave infrared band. And I picked out 3 days of wintertime observations that were cloud-free. And I picked these to get a range of different sun angles. You know, as the seasons are changing, the sun's position in the sky is changing. And so I picked out some days here to look at. So I already said, like, our satellite doesn't know the difference between what's reflected or emitted midwave infrared. So how are we going to measure a signal of that reflected midwave infrared with our GOES observations? If we imagine just some surface emitting, according to its temperature, cold at night, emitting thermal infrared, the dashed line, and emitting some midwave infrared, the solid line. Cold at night, warmer during the day, it might look something like this. But in the daytime, we know that there's also sunlight coming down. So it's going to be reflecting a little bit. So we have that total midwave radiance. And this is what the satellite's seeing. It's seeing our total thermal infrared, which is just emitted, there's no reflecting, and our total midwave, which is the sum of that reflected and emitted. If we take the difference between these, what we're hoping to get is a signal of our reflected midwave plus maybe some constant, as you saw with our whole midwave weren't exactly equal. And so we're hoping that this will give us that reflected midwave signal that we can then use to look at the shadow hiding in midwave. So next we go ahead and predict, or just calculate phase angles based on, where the satellites are, the fixed relative to the ground plane of the sky, and then compute where the sun is traversing the sky, compute those phase angles. And so I'm showing here the phase angles for the 3rd of March 2020. I picked this day in particular because this is the day where they both reach phase angle of 0, where the sun is directly behind exactly the same line of view as goes as seen as seen. So we can go ahead and plot. This is for that day, March 3rd. We can plot the midway and which are the solid lines, and the thermal, which are the dashed lines from each of these satellites. We can also already see some fun of it here. We can then take the difference between those midway and thermal bands. We get a plot that looks like this. And these vertical dashed lines are those predictions we made about when we thought this might be occurring, and that phase angle reaches 0. And if we plot that against phase angle, we get plots that look like this, very superficially resemble the hotspot plots that we had for visible and near infrared light. But now this is for midwave infrared reflected reverse. So then we looked at this for all the pixels across our site, all the different days. But we actually found that the magnitude of this effect wasn't actually correlated with the amount of forested area. We were seeing similar effect for snowy areas and for forested areas. So what's going on here? Here's an example of a mostly snow pixel. We're still getting a really strong effect here of this latest hotspot. Well, we know, thanks to Steve Warren and others, that snow in visible and near infrared can actually be strongly fast scattering or exhibit a shadow lighting effect if it's a rough snow surface. So now, instead of the scale of trees, I'm talking about the scale of little centimeters ripples and screwy wind-blown snow across the mesa, casting all these little shadows. And here are 2 pictures I took out on Grand Mesa when we were there. So one, I'm showing from the point of view, you can see those shadows, and then turning around for a different time of day, looking out there, you can't see those shadows anymore. So in chapter 3, we determined that you could find the midwave infrared hotspots or these peaks using the fit minimum daily phase angle that we know occurred. But we were seeing similar magnitudes in these peaks between the more forested areas and the open snow areas. And they're both exhibiting what looks like this midwave infrared shadow height. So where does this leave us? So unfortunately, not all snow looks like this. It's not just flat. It's not easy to observe with satellites. It's much more complicated than this. It might look something like this. So what does this mean for using geostationary satellites for observation of the snow in the forested mountain areas? What we've really shown is that you need some knowledge of the land surface that you're viewing in order to interpret the results you're getting, rather than just taking the satellite imagery and taking that for granted and saying, this is the surface temperature here. That's what I wanted to do at the beginning of this project, because I wanted to be able to take that information and say, hey, how can we improve this model? Like I said in the introduction. But the more I looked at the data, the more I kept finding these things like, oh, this isn't exactly what we thought. Oh, this is different than we thought. Oh, look, this is another problem that we're having that needs to be resolved. And so future work, building on this to try to get this skills imagery to a place where it is applicable to be used for applications like this will involve doing things like building empirical reflectance models for the area you're looking at, because it's going to depend on forest cover or snow roughness or the shape of the terrain. And this is really important and going to be of increasing importance, because I've been talking about the GOES imagers, which are operated by NOAA, but other space agencies around the world have similar instruments on geostationary satellites that view other parts of the world. So here, this is an image from the Chinese FY4 satellite, and I've just drawn a box around high mountain Asia. A lot of people live there and depend on the water resources there. And so, because these geostationary satellites are improving in their spatial and spectral temporal resolution, more and more people who are doing land surface imaging or interested in processes on the land are going to be using these when traditionally the platforms have just been used qualitatively by forecasters. We look at the images and forecast our hurricanes, we do atmospheric research, which kind of is like historical use. Another big part of this project has just been developing software tools just to work with the data. I talk about how this data is 5-minute temporal resolution, and I'm looking across, maybe weeks at a time, or even in the first chapter across several years. That's a huge volume of data, and has been a struggle and a challenge to figure out ways to work with that data. And but a lot of the tools that I've worked on are available open source, and hopefully will be picked up by others who want to use GOES data to do this sort of work. And so I hope that that can kind of continue. I do also want to thank Paulo, who collaborated with me on some of this work. He's a graduate student, so we just both were working on GOES at the same time, and found out we needed the same software to do the same. With that, I want to end with some thanks. First, I want to thank my advisor Jessica, my committee members, David, Chris, Bart online, and Steve, Bart at GSR, for being on my committee, and Jessica just for being a great mentor and giving me lots of opportunities for professional development while I've been here, like teaching that class, going to snow at development, great, going to Los Alamos, that project didn't happen. That was still true. I also want to acknowledge NASA, my funding source. I want to acknowledge the whole SnowX community, and especially the SnowX leadership team, Gary Gorovich, H.P. Marshall. They've been great mentors in helping this work actually happen, especially during that field campaign. Also want to thank our snowmobile guides and our NSIBC folks that were out there with us. I also want to thank folks at the eScience Institute, Scott, Emilio, Nicoletta, Anthony, you've all given me not just technical advice on a lot of these computing problems, but also given me opportunities to go do the hack weeks and participate in those, which is a lot of fun. Of course, I want to thank the whole mountain hydrology group and the extended Topper Lab and Fishbowl Treehouse gangs and everyone. You've made this a fun experience, past and present members, of course. Also want to thank our union, UAW 4121, UW works because we do. Thanks for, we got healthcare and stuff, so and a paycheck. And then I want to thank my science communities outside of the university, the Bellevue Parks departments. It's been able to keep me grounded literally with my hands in the dirt, pulling weeds and stuff, the Seattle Aquarium, and then Ribbit Network friends, working on some fun projects. And then, of course, I want to thank my friends and family, and especially my partner, Christina. There you go. I could have done all the support. And with that, take questions.
The way this works is we start with the general audience, and then we will send the general audience to get snacks and go away, and then just the committee will convene. So this is your chance. All of your big questions, ask them now.
Great presentations, and great work around including the athletes. I have a question regarding the use of the data. You say you received most of the expenditure, which we related to support biological models, support other related activities. Is it useful for farming? Is it useful for where do you see this going?
Yeah, I do think it is going to be very useful. It's just gonna take a little bit more work than what you've seen here to figure out exactly how to interpret that data and how to say you're running a hydrological model and you want to assimilate this data into it. What exactly are you going to compare in your model to this? Like, you don't want to just pick out, okay, I'm going to compare snow surface temperature at this point to this GOES giant pixel that covers this huge area. You may want to say like, okay, well, maybe from the model, I could like simulate what would GOES see in my model. And then is that what GOES see in real life, type of thing. And so that might involve doing things like, you know, adding in the forests and the view angle, parallax effects, and how that's biased in the GOES imagery. And because GOES is near real time, and it's used for things like, you know, looking at wildfires and stuff like that, I do think it will have, or just geostationary imagery in general, will have opportunities for like real operational use if those challenges can be overcome. Which I hope this is leading in that direction.
Given that it is kind of a location specific question, but particularly over, let's say, Grand Mesa, we have two satellites that are, you know, we're able to get two answers from GOES 16 and 17. And given the time of day, like, differences that we saw and the improved, or I guess I interpreted as like the bias increases depending on the time of day. Could you assimilate them together to kind of minimize those impacts from essentially I think their phase angle?
Right, yeah, I did look at. Oh, yeah, I'll repeat the question. The question was, because I'm seeing biases at different times of day for these two different satellites that have different view angles, what if I combine the two to get the best of both worlds? And I did look at that, and it does look good. You know, it does require you to say like, okay, throw away the morning from this one and the afternoon from that one. So you do need to know something about what you're looking at. But yeah, you need to play with the data and get it to fit until it's good. But yeah, it does require, you know, that prior information. And so, yeah, I think there is a future there. You also saw that the pixel grids don't line up exactly. You know, I picked ones that were as close as possible, but it's not exact. And so there are opportunities and challenges there. I think so. The challenges are just that they don't overlap. So if you do compare or average them or something, you're not really averaging the same two things together. But there are opportunities there. There's a technique called microscanning used in microscopes and telescopes and cameras. And it's basically where you introduce subpixel shifts to get a finer resolution. And basically, because we have two grids that are offset, we already have like these subpixels that are like the intersection of the corner of one and the corner of another. And so you could actually like maybe start to use that to tease out a little bit higher spatial resolution. Yeah.
Have you had a chance to look into the compounding effects of the shadow being cast on a steeper gradient?
No, which is why I use Grand Mesa, like you have to do that. So in the first chapter, we did try to look at this forest question on that complex terrain. And our results weren't conclusive, like we were seeing these warm biases, and it did seem to match the forested areas better. So we were like forests and mountain slopes and everything. But then again, I don't know if they were matching better because of that, or because of the terrain and the solar, you know, illumination that was also happening there. And so for visible and near infrared imagery, and even models, in fact, Bart's PhD thesis, what I read before this, because he had some shortwave modeling going through a canopy. We can actually have a geometric model of your forest and be like, okay, how much sunlight's passing through, how much is being reflected, how much is being scattered, and get really detailed about that. Which, yeah, it would be interesting to then start pointing this other places and maybe comparing against what those models are saying about how light behaves those complex areas. The short answer, and the flat area, so we don't have to think about it.
Super awesome talk. This might be a little out of the scope, but someone did a this question. So you looked at temperature biases, and I wonder what, like, implications the temperature bias has. So if you're communicating to like the California water temperature and you say, oh, well, if you actually don't correct for these biases, then you're going to model your snowpack melt date. Like, for example, in the Sierras, it melts in June, but actually it might be like 3 weeks earlier if you don't account for these biases. Have you like looked at any of the implications or like how you communicate the necessity of accounting for those in the imaging?
Yeah, great question. So the question was, if I were to talk to a water manager about this, they want to use GOES data, how would I communicate these biases we're seeing to them, how to use the GOES data? Yeah, I would say like if you were just looking at these observations and thinking this is snow temperature, you would be thinking like, oh, all of our south facing slopes, or not even south facing, all of our slopes have melted out.
Yeah.
When really it's just the south facing slopes because these observations were biased, from that point of view. And so it would be things like that, like you need to know, yeah, like the map I showed earlier where I classified the land surface. There are parts of the mountains we can't see at all, like behind another mountain. And so it's like, we definitely have no information about what's going on there. And so I think that's like a good example to show like, yeah, these observations really do need context and information about the land surface, which like for observations of a place that doesn't have like LiDAR maps of the forests and stuff, could at least have a terrain model. We have those globally, but that would be complicated and more than that. Yeah.
Was there any consideration to, given that you're trying to take low performing or airborne data that's always nadir versus the spot nadir view from the GOES satellites, to change the sensor package, and it could be easier to do it on the aircraft than the satellites, but so have it fly offset at an equivalent angle and get the higher resolution at that angle?
Yeah, so the question was if we considered or looked at having our, basically like our validation data from the aircraft thermal IR images, if we could point those in the same direction that GOES was looking and see if they match better that way. So Chris might have a better answer than this, since it's his instrument that he's so graciously letting us use, but it does have a pretty wide field of view. And so we do get some pretty far off later views on the edges of like the image swaths that we're getting. And I did look at, we didn't plan it this way to like do any like observation things like that. We should have, but I did look to see if we like happened to get any that way, or if we happened to get shadow hiding in that imagery. And the way we were flying, we just weren't. Those angles weren't high enough.
Yeah.
We really would need to point the camera to do that, like even though it is scanning a wide area. Yeah, that's really what you want to do. Although I did make an offer to someone. I said, you could be a co-author on my paper if the other idea would be to take those temperature maps, drape them on a detailed LiDAR map model of the forest canopy, and then you could simulate views from all sorts of things. So if anyone wants to do that, there's still co-author position.
Online.
Oh, great.
Steve, you can unmute yourself if you'd like to ask yourself, otherwise I can read it for you. So Steve asked, for a given pixel surrounded by n pixels, how accurately can you determine the median surface temperature and the range? Could you then model the n pixel domain as uniform probability?
Yeah, that's a great question because our pixel grid that we're using here has actually already been resampled, which complicates some of this analysis. The actual image sensor is slightly finer spatial resolution, but when they go from the raw data into the final image product, they do a resampling step. And they won't tell me what that is because it's proprietary to the manufacturer. And I've asked over and over what that is, and they won't tell me. So maybe I need to reverse engineer it or something. But, so I think that's adds uncertainty to knowing what is the median temperature in this pixel, what is the range of temperatures we're getting, and how that's related to the pixels around it, especially if they actually have overlap rather than the way I've drawn them where they're nice little boxes. These pixels are actually probably sampling a little bit larger areas.
So question about the temporal resolution, is 5 minutes like perfect, like enough to observe all the kinds of stuff that you might want to observe, or do you want to go higher than that?
I would want to ask a hydrologic modeler or whoever's using the data, like what application it's for. I mean, you see a lot of hourly models, and they're like that resolution, you know, you can capture these things, so maybe that's all you need hourly, but it really depends on, yeah, what your application is. The other thing is some of that high temporal resolution might help if you do temporal resampling to cut down on noise. I'm not convinced that their satellite pointing is as stable as they think it is. I think it wobbles a little bit, and so doing some smoothing in time might alleviate some of those issues. So yeah, having 5 minutes. I mean, honestly, it seemed like overkill when I was doing this. I mean, our ground sampling equipment doesn't usually do 5 minutes, but I said it to do 5 minutes because I really wanted to see. And I said something to do like 1 minute and just getting it faster. So yeah, I think this application.
Good talk, so you can really go there. I have a question regards to snowpack properties. So, you know, we went out to Grand Mesa, middle of winter, like smooth surface, and now thinking about, you know, different snowpacks around the world, being the tundra, we need like, you know, established one. Do you think there's any limitations to apply this method to like an early snowpack or just like a deep winter snowpack or something like that?
So there, I didn't touch on emissivity in this, and I will get in trouble for not mentioning it, but emissivity is it describes how much radiation a surface is emitting relative to like a theoretical ideal emitter of radiation. Snow and vegetation are both really high emissivities, but snow does vary, especially with dew angle. And so, but also with grain size. So as the snowpack is evolving over time, grain sizes are changing, growing, it's warmer, or new snows that possibly on top. That could change some of what we're seeing. The emissivity would actually introduce a cold bias in a lot of our imagery. And so the biases we're seeing may actually be larger because these images might actually have a little bit of a full bias pretty added to them. And so, yeah, different snowpack, like snow grain properties like that, but also snow roughness, like with the snow we saw in chapter 3, the little centimeter scale bumps, you know, casting shadows. You know, but if new snow falls on top of that, it's smooth again, and we may not be seeing that effect. If it's windy again, if the road's bad, I think this stuff, it changes really quickly, which is why I was saying like empirical models based on observations are probably needed to really interpret it. Like what did it look like yesterday, and use that to inform today, and that's probably as best as we can do.
All right, let's thank Stephen. And then let's take a 5-minute break, and I think we should shut down this Zoom and then just send Bart an invite to a personal meeting room. Especially, but the thing is, we want to start a new Zoom room, trust me. And so Stephen can say goodbye to anyone on Zoom in the next